Hello and welcome to this video. This is a very short introduction, a very basic introduction to calculus. In this video, we shall be talking about an introduction to calculus in a way which is more suitable to, people who are doing not an in-depth course on calculus, but rather just as an application purpose in other fields like physics, for example. Okay, so calculus is fundamentally different from the mathematics that you have studied earlier. It is less static and more dynamic. We shall make it clear what it means actually. Calculus is also concerned with change and motion. It deals with quantities that approach other quantities, that introduces to the idea of something called limit as a historical perspective. This calculus, it came into the form, or at least it was known in some form to the ancient Greeks at least 2500 years ago, when they tried to calculate the area of polygons by dividing them into triangles. This method was known as a method of exhaustion. It was extremely difficult at that point of time to compute the area of curved figures. The other motivation for studying calculus is the problem of finding the slope of the tangent line to a curve at a given point. We already know the idea of tangent line to a circle, for example. The idea is that by definition, the tangent line is going to touch the circle at exactly one point. This definition, however, doesn't hold true for more complex functions over there, more complex curves. So that is one area where the calculus, the differential calculus, comes up over there. As an application in physics, for example, the calculation of velocity, or for that matter the acceleration, it involves the idea of calculus. Now, in the heart of this calculus, the most fundamental idea that we shall be talking about is the idea of functions. Now, what exactly is a function? In general, a function is present wherever one quantity changes because of a change in another quantity. For instance, we can have changes in pressure as a function of the height. For example, as we go above the Earth's surface, the pressure varies. So that represents a functional form of the pressure with respect to height. Or we can consider a more, example which is more familiar. Basically, we can think of a person who is going on a ski, and the hill which is covered with ice that undulates a bit, and as he goes away from the highest point, the undulation of the hills, the height of the hill from the mean level, the ground level basically, is going to change. Okay, so this is the basic idea. The basic idea is we will have a function or idea of function wherever or whenever one thing varies with respect to the other thing. Fine. Let's try to be more precise. In general, a function is consisting of a few things. First of all, there is a set which is called a domain set. Let's call it as A. So A is a domain set. Then there is a function then there is the codomain, another set basically, and then there is a rule. The rule which relates an element from the set A to a unique element in set B. So this rule is basically what we often think of as a function. However, the function actually consists of all the three components. It has to be a set A, a set B, and the rule. The rule, what it does is going to associate every element of the set A with a unique element set B. So the idea is there are, first of all, you can say that a function is basically a rule, and this rule, what it does, it assigns every element in set A to a unique element in set B. The keywords in this case, there is every element in set B actually. So the keywords that we have over here, they are every and a unique element. So what it should do basically, the rule is going to first of all associate every element in set A. So no elements in set A can be left out actually, and to every element in set A, it should associate a unique element in set B. It can't associate two elements in set B to the same element in set A. So for example, if I have a pictorial view, suppose for example A is a set consisting of these points, while B contains these points. So this rule, what it can do is, it can tell us exactly, for example, this point is associated to this point over here, this one is associated to this point. We might have two elements of A associated with the same element in B, and then we can have like this. So this kind of picture or pictorial diagram give us a function, because in this case it tells us exactly how or what rule this particular function follows in assigning the elements in set A to elements in B. Fine. Most often in our case, A and B are going to be domains, or A and B are going to be subset of real numbers actually. So we shall call these functions as real functions. So they are basically real valued functions. For every element in A, for example, if I take an element X, then the corresponding element in B, which will be associated with, is going to be called an fx. Fx can be thought of as the value of the function at the point X. So as I said, these are real functions, which are implying that these are real valued functions and defined at real points. So in general, A and B are going to be some subsets of real numbers. Now, representing functions, one very useful way to deal with them is to represent them as graphs. So we can have basically a rule. For example, suppose we consider a rule which is associating every real number X with a number which is twice X minus X square. So this is a rule. It tells us that every element in the set A, which in this case is nothing but the real numbers, should be associated to a number which is also a real number, but that is obtained from X by operating X in this fashion, 2x minus X square. So this is an example of a function. This is an example of a function. We could write down the functional form, in this case fx, as 2x minus x square, right? Now, if I want to draw the graph of this function, what needs to be done? First of all, what I can do, for example, is I could take a series of values of x, mark them on the x-axis, and associate the value of the function at the corresponding point x with the y coordinate. So I could write down basically y as fx. This will give us the graph. So basically what's being done in this case is we are going to find the value of this function at every x and assign that particular value to the y coordinate. For example, in this case, if I plug x equal to 0, then I get fx to be 0 as well. So the y coordinate is assigned a value of 0 when x is 0. So the point becomes 0, 0, which is a point of the graph. I can put x equal to 1, in which case we shall end up getting 2 minus 1, that is 1. So the y coordinate is 1 as well. On the other hand, if I put x equal to 2 in this case, let's write down the values. Let's map it over there. So basically we have the values of x and the corresponding values of fx, which I'm associating or assigning to y as a y coordinate actually. So if I put x equal to 0, I end up getting y 0 as well. So the corresponding point is 0, 0. If I put x equal to 1, for instance, then y is also becoming 1. Well, that means that it's going to be y equal to x for every x, by the way. Okay, because if I put x equal to 2 in this case, we notice that when I put x equal to 2, the value of fx turns out to be 0 once again. So we get 0. Obviously, drawing the graph will not be done only by using these 3 points. We shall require more points. One way to draw the graph is to utilize a computer, for example, or a graphing calculator. Or the other way we can do is just taking a series of values of x, a large number, correspondingly large number, then finding out the y values and then noting down the points x, y in the xy plane. That should give us the relevant graph. Fine. Let's try to draw the graph for this particular function. As I said, in this case we shall require more points over there. A brief sketch, for example, we could do. What we have over here is, I have just noted down the x and the y coordinate. For x equal to 0, the corresponding point is 0. For x equal to 1, I get 1 as well as the y value. We get a point 1, 1. This is 0, 0, and that is 1, 1. But then if you put x equal to 2 in this case, I'm going to get back 0. So I get another point over here, which is 2, 0. I can draw other points. For example, if I take x equal to 3 in this case, with that value of 3, I end up getting 3 to the 6 and minus 9, which is minus 3. So at x equal to 3, we end up getting a value of minus 3, which will be a bit down over here. That's the point we have. We can just take more points. For example, if we put x equal to half in this case, then the corresponding value becomes 2 into half, 1 minus 1 by 4 is 3 by 4. 3 by 4 is lying somewhere on this side. So in that case, I shall have a point over here. I could do that for the point x equal to 7 by 4 as well, which is just 1 4 less somewhere over here. So corresponding value turns out to be the same as 3 by 4. I can put x equal to, for example, 2.5 or 2.1. I can just go on putting different set of values, and for each of them I will end up getting a certain y value. So if I have got enough number of points, I can just join them in a smooth manner and end up getting a graph which looks like this in this case. This is nothing but a parabola actually. This is the graph of a quadratic expression in fact. Right. We can look at some other functions. We can have, for example, piecewise functions where a function is defined by different set of formulas in different intervals. There are some basic functions that we should be keeping in mind. These are basic in the sense that they are and they can't be expressed in terms of the other functions, but the other function can be expressed in terms of these. So in that sense they are fundamental or basic functions, elementary functions. We have one which is the power function. The power function is in effect fx equal to x raised power n for some power n, and may be an integer, it may not be an integer. The other function that we have is the exponential, the general exponential, which is of the form a raised power x for some base a which is positive but not equal to 1. Thus by definition require this. We have something called a logarithm, which is written down as log of x to the base a. Again, a has to be positive and not equal to 1. Then we have the trigonometric functions, which there are 6 of them. We shall see them later. And we have finally the inverse trigonometric functions, these are 5 basic categories of functions. These are basically well known. Other forms that you could get, for example, by combining power functions, we can have polynomials, which are very well known functions actually. We know quite most of things about the polynomials. Then we can have, by combining polynomials, something called rational functions, which are simply the ratio of two polynomials, very analogous to the rational numbers themselves. We can have some other piecewise functions, which are defined by different analytical formulas in different intervals, right? In general, we shall be looking at some very simple functions, though functions can be used in a wide variety of situations to model different physical scenarios or geometrical scenarios. For example, we can have the area of a circle, which we know is pi r square. Therefore, I can think of the area as a function of the radius. I change the radius and the area changes as well, right? We can, for example, consider, as I said, the height of a roller coaster, for example, as a function of the distance along the base. That can again be thought of as a function. You should keep in mind that the graphs are drawn for equations. Okay, we have, for example, say a linear equation x plus y equal to 1. Now this is only one equation and we have two unknowns x and y, as a result of which we don't have a unique solution. In this case, we will have infinitely many solutions. So if I just plot the solution as points of, if you just plot the solution on the xy plane as pair of points x comma y, that gives us a graph of this equation, right? So every function has a graph, but not all graphs can be functions. In fact, if I have a graph which, for example, bends back onto itself, for instance, if I consider a function which is a graph which is like this, for instance, now this graph cannot represent a function because it violates one very important principle, which in this case is the fact that for a given x we can have only one particular value of the function, but this function assigns two values, in fact at least two values, in fact we can have more than two values to the same values of x. So this can't be a function. So you can think of it like a vertical line test, where we draw a vertical line, and for the graph, if it is to represent a function, should intersect the vertical line at most one point, right? So that was a brief introduction for functions. We shall continue with this idea of limits in the next video. Thanks for watching.